But final would be similar to midterm. Same format, same expectation. You know, just as long as you're very careful, you can do it well. Careful meaning careful to implement the plan. There's no surprise about the plan. But neural networks is bigger model. It's 5 times more lines of code. If you make one mistake in the middle, and in the middle of the exam, it's hard to debug. So practice that process. Be prepared, you'll do well. So final exam, not really something to really worry about. But project is fun and challenging as well. So, and you can get a lot from it if you try your best. Today, mostly the purpose to cover homework 4, right? Not specific to talk about homework 4, but these are really to help you understand what's going on about these points that are relevant to homework 4. I went back and looked at the videos particularly. So there is video. Let me show you. There is video on regular expression. I think Lily said so, and you probably know, right, Megan? There's regular expression videos, and there's a question. There's a big question with several questions in it in the homework about how to construct a pattern to identify, to find all these different symbol strings. And with the stuff I covered 2 weeks ago, I think you should be fine. And then this is more about cleaning the text data, not even to pre-process. It's cleaning those symbol strings that are not helpful at all, simply not helpful. And these symbol strings get into the data because it's data is scraped online from HTML. So there are these problems. We use regular expression to deal with it. You don't have to, depending on the scope of your problem. If the data set is very small, limited, and the kind of symbol strings are highly expected, you can simply do a literal search and replace it. Regular expression is a powerful tool that may come in handy in the future. I don't know, maybe one of your interview questions asks you about regular expression. You cannot know nothing about it. You have to know the basic things, and that's probably enough. If you need to learn more, learn those when you have to deal with more complex problems. But all of these that we talked about here are very basic use cases of regular expression. You know how to use this, you should be fine for now. So that's cleaning. And after the cleaning, you need to pre-process the text for modeling the text data. And this is both for supervised learning and unsupervised learning, because there is certain steps that you have to do about these texts before you can do anything modeling about these data. These text data are not in numeric formats. You simply cannot put them into the algorithm. So this is a process that they call encoding. Before, let's say there's another language, a foreign language that you want to understand. The first step you need is translation. Before translation, you just cannot, there's no way you can understand it. So this encoding process is like translation, to translate texts into numbers so that computer can try to crunch the numbers. So this is what we call pre-processing here. And pre-processing includes steps and techniques such as tokenizing, lowercasing, stop words, stemming, Limitizing, things like that. Or, dealing with high frequency and dealing with very long, unique tokens. So these are pre-processing. After pre-processing, then you can start with more specific modeling tools. I think these are intuitive, but just to give you an example, in our daily usage of language, well, let's say if language is going to give you any useful information, you only have to pay attention to certain words, but not the other. Right? In almost every sentence I say, I'm going to say the word to, T-O. I'm going to say the, T-H-E. Words like these don't help. Even though, as human, we need to have these embedded in the sentences to really know what I'm talking about, or at least to know what I'm talking about without any difficulty. If I skip those words, you probably can still guess what I'm talking about, but you're going to say, anyway, say English. Because, if I skip those words, I'm not saying English. So for humans, that's good. But for machines, they really don't need that because these words don't carry information. Words that carry information meets two criteria at the same time. These words cannot be too common. Stop words are too common to carry any information. And these words cannot be too unique as well. If it's too unique, maybe a typo. Typo doesn't help very much. Like, if this article is about a foreign country, let's say Spain. So it talks a lot about Spain. It refers to the name Spain, the country Spain a lot. So this word is not extremely common because this word doesn't appear in many other articles. But this word is also not as extremely uncommon. If you accidentally put an A after Spain, S-P-A-I-N-A, Spaina, this word doesn't appear in any other article. Model could think too much, saying, this is a unique word, this is very important, but it has nothing else to correlate with. So this word is not very useful as well. So it cannot be on the either extreme. So we want to exclude those words that are on either extreme. To allow the more significant pattern to surface from the vast, space of dimension, because there are just too many, a large number of words for the pattern to be detected. It's a large dimensionality problem. Anyway, but there's no homework on these tasks. There's no homework on tokenizing. There's no homework on, almost anything that's related to pre-processing. So it's kind of like, these are very important, but you're not doing any questions on these, and not in the final exam. And this is because this course is already covering a lot. So I'm not going to test you on every aspect. So I gave you the clean data set for those questions that are after question 5. Thank you. Right. So all the questions after, starting from question 5, is specific about modeling. Right. The unsupervised modeling, LDA part. So be aware that what I'm going to talk about here in terms of pre-processing the texts, there's no homework questions about them. But I will, in the middle, because I think it's still very useful. It's good to know about these, and you can review the video afterwards if you need to. So I'm going to try to make it more fun. And I'll have some bonus questions in the middle. Just pop up bonus questions. If you follow very well, there will be the rewards. Because I really want you to pay attention, and it's useful. All right. So just a little bit of brief overview. Tokenize, what does that mean? Tokenize is to break it down, break the text down into smaller units so the computer can process one at a time to differentiate different chunks of information so that it can make better judgments. The most common way of tokenizing is word-based. Each word is a token. Token equal word, basically that. So different words means different token. If it's the same word, appearing in different places, that's two instances, but that's the same token, right? Think of an English dictionary. Every term is a token, but there are also other levels of tokens. You have 2 gram. So single word token is 1 gram. You also have 2 gram, or we say bigram is 2, right? Bigram, or 3 or more. N-gram is a general way to describe it. Why do we need that? Because early natural language processing models only use 1 gram, and it's already complex enough. It's more than what a computer can take, or more than what the algorithm at that time can handle. So 1 gram is no more, just 1 gram. I'm okay, fine. There's only limited information that can be extracted. But as the computer science domain evolve, they start to hit a plateau, hit a bottleneck. 1 gram allows a well-designed algorithm to extract this much information. It's hard to improve further. So they need to look for areas for improvement. So the area for improvement is maybe we should start thinking about phrases, not only words, because that matters. If you only pay attention to words, then that means if you switch around the word order, that's the same thing. A sentence is made up of words in specific order. So word order definitely carries information beyond a combination of those words, for sure. But it's harder to consider phrases because you cannot pick what is ex ante. So you cannot assume which part of the sentence is more important phrases. So what you have to do is after analyzing each word, you have to take sliding window of 2 words and create these additional tokens. And think about how much more tokens you have to handle. It's almost double, right? It's almost double. Sliding window of 2 words, like 2 word phrases. Now, I like Python very much. You have to include these 5 words. And you have to include I like Python. Python very much, Python very and very much, 4 more. It's almost double the amount of tokens that you have to process. And with longer word sequences, it puts a more text on the memory. So early stage computer science equipment cannot handle them very well. But as the equipment gets improved and algorithm improve as well, data size improve, you start to evolve. So this is kind of what happened. But in this course, we deal with 1 gram. Lowercasing, always do it first. As we'll demonstrate in the demo material, lowercasing is the first thing to do. And it's just part of the steps. And why lowercasing? Cases may make some difference. Like, Chinese. No, not China, China, okay. Capital letter China is the country. Lowercase China is the the ceramic. But these cases are too few. There are only a few limited, words that fall into this case. To generalize this rule to every other word is too much generalization. So we assume the amount of gain to treat capital versus lowercase differently is outweighed by the amount of add-ons to the model that will lower the performance as well. So it's not justified. So we convert everything to lowercase. This is in English though. If you're dealing with French, Spanish, or other things, that may depend. But in English, almost always convert it to lowercase and be done with it. Terms of extreme length. This is, I think, as the domain evolved, this is what they discovered. For English, words of 2 letters or less, words of 1 letter, a limited number, A. What else? Nothing else. Maybe something else, I don't know, but these can be safely excluded from the beginning. Words of extreme length, these are unique terms that are very specific, very technical, almost never happen in more than 1 or 2 articles. If they happen so infrequently, the algorithm is not able to pick up patterns there because it's just as if it's randomly popping up here or there. That's it. And there's not enough data to associate that with anything else. If you try to associate too much, it's overgeneralizing. It doesn't work. So extreme length words that happen only once or twice in the corpus doesn't help. So we'll exclude them. So you pick the boundary between 3 and 15 is fine. Why 3? 3 is quite common. Why 15? You can change it. 14, 15 doesn't change too much. Take a distribution of the English Wikipedia words and look at the distribution of the number of characters in a word. The majority of them are between 3 and 15. But whether or not you use 15 or 14 doesn't make too much difference. You can try it out. You can compare the results. Not too much difference if you're working on a small data set. So that's why. And then excluding the stop words. Stop words, it's not a long list. English stop words are between 200 and 250 words. That's it. But they occur with high frequency. And they don't carry really any meaning. They are functional words that make the language smooth and human-like. For computers, you can sacrifice the little bit of what we say syntax, English syntax with the stop words. It may have somewhat additional level of meaning if you include them, but if you remove them, you will gain a lot in terms of computational efficiency without compromising too much of the syntax. Maybe after our computer has, if all our computers are powered by quantum computing, maybe we can start to put in stop words, maybe, and we'll have different generations of algorithms that will compute with the presence of stop words. But our current algorithms assume that stop words, most likely it's been removed, right? And lemmatization versus stemming. This is in terms of the word tense, like past tense, past present tense. Liking, I liked. They kind of, say the same thing with slight differences in tense. So there are packages, in natural language or in linguistics, this is a big deal. You want to convert them to a standardized and remove the tense because, again, these variations carry a little more information. So, but for computers, if you don't transform these to the original tense, computers thought these are two different words, like and light. They're different, but in fact, they are the same. So, maybe better off if you lematize. But empirically, you have ample room to argue either way. I have seen cases where using lemmatization is better. Other cases where lemmatization doesn't help or made it worse. It's a puzzle why that is the case because I just cannot describe and understand in a complete picture how computers work. It's just computer algorithm go far deep into the data to the level that we cannot comprehend. I cannot comprehend. So I don't know what's happening. But what I do is I compare both, one with that and one without lemmatization, and I take a look at the test set's performance and let it judge. So I would say in common practices, you just make a decision based on convenience. If it's convenient for you to include it, you include it. If it's not convenient, you don't include it, and it doesn't make too much difference. For here, we are picking inconvenience. The previous version of the course included it because the package included it very easily. The package got upgraded in the winter, and the original original function for lemmatization didn't work anymore. So you have to make a choice. Either you use the upgraded version of the package, GenSim. GenSim, I don't know what it means, general simulation, could be, but the GenSim package got upgraded to version 4. Lemmatization is dropped. You can do stemming, but stemming has other limitations as well. And same problem. There are cases in which stemming helps, and stemming didn't help and made it worse. So because of convenience, I chose not to include lemmatization. The final result in terms of the LDA model, you almost notice little difference. Just tiny little difference. So I don't consider it's deal breaker. So that's why we're skipping it every time. But I still include in the slides or the demo just to comment them out. Didn't make any effect. Just in case they put it back, we can just quickly swap the codes. But so every time you see the grayed out content, it is about lemmatization, and we're skipping it. And lemmatization is related to part of speech. If you know what part of speech is, different tense and different tense and as well verb versus noun versus adjective. Different purpose of the words. These are non-stop words. They're not stop words. Okay, so we're skipping that. In terms of natural language processing packages, Nltk is a very powerful one. It has more functions than what we're going to use. It is more traditional. There's an R package for Nltk. In fact, I learned Nltk in R initially, and then they also have it in Python. So early stage of natural language processing or linguistics, actually, they use R, and later Python pick up, because we're really using it for modeling, not really dealing with linguistics related tasks. GenSim is more targeted with support for LDA at a very intuitive level. So makes learning the model easier to explain. So we're using GenSim. Okay, so the demo, I will go through at the code level rather quickly and have some bonus questions to really try to understand the process. We'll do lowercasing, which is very easy, just one sentence. But tokenizing and different alternatives for tokenizing, and then removal of start words, and also removing all the numbers. And in the end, we'll put them in a pipeline, similar to the way we'll put together a pipeline for pre-processing the numeric data sets. So pipeline makes it very easy to reuse the code on new projects and new data sets. So let's switch to demos. Okay. So I'll begin. I'll start from after using regular expression and start with GenSim, and also simple process. Right, start with GenSim. No, wait, hold on. Not yet. There you go. Motivating example here. So this is a typical document, we say, a text string that is, a piece of data. Let's say, a review, a comment, somebody's comment, or a paragraph. This is the original text. Text, you can see uppercase. You'll see some punctuations, sentences, comma, and period, punctuations even. This is the punctuation inside the text, not the punctuation, not the quotes that's around the strings, but in the actual text. So we need to remove them. Put it in Markdown. It's easier to see there are numbers, uppercase, lowercase. And so import these tools. I commented out the limitize, but keep everything else. Okay, to do lowercase is easy using the string function. .lower takes care of things. We'll keep that in all the following functions. So that takes care of everything. And just to demo that for the motivating example, after converting lowercase, it's all lowercase, and nothing else has changed. And then next is Tokenize. Simple Tokenize combines multiple operations, actually. Simple Tokenize will take care of the lowercase as well. But I here include lowercase because eventually we'll have to still include it, because we'll not use simple Tokenize. We'll use something else that includes additional functions. So as a good habit, you include lowercase. It's not as if you do twice the lowercase in, it will become uppercase. It's not like, minus becomes positive. It's nothing like that. You do it twice, it's still going to be lowercase. So you put the lowercase text into simple Tokenize, you get something. That something is not text, actually. It's an object. Makes it mysterious, but it's more efficient in terms of data storage. So that's the way it goes. But even though it's an object, you can treat it as if it's a list. So when you pre-process a text, a good process would be to take the text, do a bunch of processing, return text in a similar fashion. You take a paragraph, you do a bunch of processing, return a paragraph. The only thing that's changed is you have removed the stop words. You have removed short words or extremely long words. You have removed punctuations. You have lowercased everything. And that's it. So you take a paragraph, you spit out a paragraph. So that's why we use the space.join. When you process that with the simple tokenize, it becomes sort of like a list of clean words. And you want to stitch them together back into paragraph. That's why we use space.join, that list-like thing. And then the S1 is the list-like thing object. You stitch them together and you print it. It's a cleaner version, right? Now we don't have punctuations. We will have in lower cases for all, and it's harder to understand for humans, but better for computers. And what else? We don't have some of the numbers. There are numbers, and now we don't have them. Why? It's not a bonus question, but because 7 or 10, they are too short. They are tokens of length 1 or 2. And length 1 or 2 are, by default, it's removed by simple tokenize. So that's why it's, I don't think so. I don't think so, no, because I is still here. So I think what's happening is the numbers are excluded, basically. So if a token is completely made up of numbers, it's dropped by simple tokenize. Yeah. Okay, so that's that. But we will switch over to a. Can you suppress? Maybe not. You just simply don't use it. You use a different tool. Yeah, I don't think that is something. Removing numbers is something that, because simple tokenize is really designed to be simple. You don't specify anything else and use it for your purpose. If it's not for your purpose, don't use it. That's why we're not using it, actually. We will use simple preprocess. I think simple preprocess doesn't convert to lowercase, so that we still have to stick with lowercase. But what it does is tokenizing. You can specify variable length to exclude. That's why we use it. We specify minimum length to be 3. Anything below 2 will be dropped. Maximum length of 15. Anything beyond that will be dropped. So that's what we get. And now we don't even have I. We don't have am. So those short words are excluded. And continue to make progress. We don't have to define stop words. There are some functions in some utility functions in GenSim that includes removing stop words as part of its function, but those functions have other limitations, so I'm not using them. We'll use it here, but use a list comprehension coding style to remove stop words. So this is the way we'll do that. List comprehension I mentioned. If you have background in Python, it's easier for you to pick that up. If not, you can try, of course. If it's too hard, you can give up. But you can simply copy the code and try to, work with it. But the way list comprehension works has been translated into this process. What the one-line list comprehension is doing is what these 4 lines are doing exactly. So if you try to understand these 4 lines, then you can understand them. now you understand what list comprehension is using, and try to adapt to list comprehension. You can start to use them from scratch even. Certainly, if you copy the codes, you can adapt to them. So that's that. What I'm doing here is simply to pick out all the list, all the stop words in this text according to a stop words collection. So after turning them lowercase and after using simple tokenize, it's simple tokenize, not simple preprocess. It's different, right? After simple tokenize, all the numbers are gone, but all the stop words are still retained. After this tokenizing, I do a list comprehension to select all the words if the word is found in the stop words collection. The stop words collection is imported from somewhere, from GenSim, I think, or maybe Nltk. Let's see. It's somewhere here. Stop words are imported from GenSim. Right. So, and then I print them one by one. Words such as the, of, this, that, I, to, of, these are stop words. They don't carry specific meanings, so we can safely remove them. To remove them, you change the list comprehension, the if condition, change it from in to not in, and they will be removed. What's remaining is the non-stop words. Make sense? So you have this this long line. The result of this line that includes lowercasing, simple pre-processing, and removing the stop words. The result of that is a list of words that you want to retain after completing that several steps at once. And then you use you use the string function to glue them. Becomes a clean paragraph. So this text right now, it's all lowercasing. It doesn't have punctuations. Doesn't have short numbers. It doesn't have stop words. That's clean. So for us right now, that's the end result of the pre-processing. We don't do lematize anymore. If we do lematize, we will change things like this. Results will become result. Because it's plural, it will be, transformed to the singular case. Indicated will become indicate. The past tense will be removed. And you will also have the POS tag. Result will become noun. Indicate will become verb. We'll have that tag after that. But those tags, even though it makes it super confusing for humans to read, it makes it easier for computers to process and adds additional information that actually helps. So that explains why that actually helps not instead of impeding the learning. Okay, so we need to do all of these. We also need to do removing the numbers in case there are numbers inside, like bit numbers. A million, one followed by 6 zeros, like long strings of numbers. We don't need those as well. So there's a specific function here which does that. Is strip numeric. If it's not for strip numeric, the standalone function, we don't actually have to use a pipeline because one line of code will do everything. If you have to do the lemmatization, then you have to use the pipeline. And now because of the strip numeric, we need to use a pipeline. A pipeline combines multiple functions or lines of codes that cannot be combined into one line. Like the situation here, we have at least 2 components to process the data. We use the pipeline and leverage the preprocessed string function that can leverage a pipeline structure. This is the pipeline process. This is the actual string. You put that into the pipeline process, and still remember to stitch it back to a paragraph still. Then you get a clean paragraph by doing everything at once. Okay, now something tricky, because it's a pipeline, you have to invoke the process string function to be able to use the pipeline. And the pipeline, the process string, the preprocess string function applies to a single string. Okay, it can only be used on a single string. But your data set is a data frame with one column, each row being a string. So you cannot use that function directly on that column. So you have to invoke that apply function, which is item-wise function for series, right? For data frame, a series. You have to invoke apply function and use that preprocess string function that invokes the pipeline. And a very long sentence for me. Anyway, so be sure you understand that. Take a moment to try to understand that. But if you do that, here it only uses one string. There's no apply function here. But later I will show that. Here we deal with the real data set. The data set has 15,000 rows, 12 columns. The column of interest would be the review text. This is a giant column with a lot of data in it. If you take it out, you can see a few rows, full of the text.
So in this last column, there is 6:15 p.m., right? And if you use the numeric in the top in the program, you used a numeric function. So it removes all the numeric data. And what happens to the numeric data that is important?
You're talking about modeling, in the sense that can we use the text data and numeric data together?
Yes.
Right. Of course. How do you do that? Let's see. So for LDA, you will not use the numeric data because they carry qualitatively different information. The task, I mean, the LDA model is specifically designed for analyzing texts. So it's designed to understand the text. Once you understand the text, you can try to combine some of the text features with the number columns. You're talking about these columns, like stars, things like that.
Yeah, in this one, you numeric one. Use the strip numeric.
Okay, no, strip numeric. Let me explain. Strip numeric doesn't strip these numeric columns. It strips those words in review texts that are purely numbers.
I understand.
Yeah.
So when you go below in review text, there is a column in which you will apply that function, right?
Yeah. Review text. Yeah.
The last row, there is a statement. Went here for dinner around 6:15 p.m.
Oh, like these?
Yeah. So what happens to those numeric?
These will be stripped. These will be stripped. Yes. If you believe, this is more feature engineering task. If you believe these carry information that are useful, then what you want to do is to develop some programming to identify these occurrences and to analyze the pattern and identify these and create additional columns to mark these incidences before you start cleaning the text. Or you can simply not remove the numbers and let the numbers potentially help you or drag you, maybe. I think the hypothesis is it will drag you more than help you. But if you really believe for this problem, it's going to help you, you can leave them in. Or if you don't want to leave the other numbers, but only the numbers that talk about time, you can develop some program to extract these time patterns before cleaning these text data and create additional columns as features to mark these before you clean them. That's the best practice. Yeah. Otherwise, these will be wiped. It will be wiped for sure. Poor guy. Okay. And so these are regular expressions. I didn't talk about these particularly, but hopefully you can piece them all together. And this is simply also using a nice process to continuously clean them based on multiple patterns. You need all three patterns to clean them thoroughly. So I'm using three patterns to continuously, clean the same, but I make a copy first in order to not change the original data, right? Make a copy and continuously feed them through different pattern regular expression to replace those characters. In the end, I replace the original column with the clean ones. So these are mostly for cleaning. And beginning here, it's really about pre-processing. If you take a look, it's very similar. It's almost identical to the codes that I show you above. This is a pipeline process. It has two steps, but the first step is really comprehensive. Includes lowercasing, simple pre-process, which includes tokenizing, removing extreme length characters. Extremity is defined here, and it uses list comprehension to remove the stop words. But before you do that, you also have to stitch it to. Let's see. No, that's afterwards. So these are together. Hold on. Right. Okay, so this is a list comprehension. Anyway, so this is the list comprehension. Includes all of these, and then remove the stop words, and then put them together as a list-like object. Use space to glue them together, but you will need to include lambda here because you are applying the pipeline on a series. And then the second part would be to strip numeric, and the outcome is still a list-like object, right? So the outcome of the pipeline is a list-like object, and that's why after that pipeline, you still need to glue them together. The result will be a series of clean paragraphs. Okay, it took very short time to do that. Then if you randomly sample, these are the clean text. Good spice, great flavor, chicken disappointing, red peppers. I don't even know what's disappointing here, but that makes it hard for humans to read. Anyway, so any questions about the cleaning part? Not the cleaning part, the pre-processing part. All right, you can watch video again, or play around with the notebook. So the next topic is Latent Dirichlet. Let me talk a little about the conceptual side. So LDA, if you're into data mining, you'll probably hear it. LDA. So what kind of problem does it solve? So basically, it's designed to summarize large chunks of texts and make searching easier, more meaningful, more efficient. Now imagine you have a large library of documents, and these documents don't have titles, or even if they have titles, they may come in with the author's own bias. You know, when you write a title for your own article, you're probably putting words to make this title more attractive to attract others to read, which not necessarily honestly reflect the content of the article. Catchy titles, if you will, So those titles may be misleading if you were to ask the authors to come up with them, and these articles don't have abstracts. So don't have a summary that allows you to peek into the content very quickly. What can you do? If computers can help, for sure, it's a good thing. So language models are basically early generations of language models try to do that, to better understand the relationships between words and documents, and how, to come up with ways to understand the relationships between the words and between the documents. And text mining is a daunting problem for early stage computer science problems, because it's just, it requires a change of mindset. If you were to try to use regression to model, text data, how would you do that? Let's say if it's also a supervised problem, and you have different articles, you're simply trying to decide or try to train the algorithm to understand whether or not this article is talking about positively about, the candidate. Different articles, articles may talk positively or negatively about the candidate. How would you do that? If the only data here is the articles, how would you do that? It's one column of text. There's no numbers. How would you do that with regression? You have the target, yes. Let's say you have the labels. How do you train that logistic regression? Let's say you have a clean, text. Everything is prepared. It's lowercase. There's no stop words. Maybe even with stop words, it's easier for humans to learn. So with stop words, with punctuations, how would you do that? It's a giant column of text. The natural way to think about it is that if you have a data point, I support this candidate. This is the first data point. Let's say this is an article. This is a very short article, but it expresses an opinion, and the label is very clear. It's supportive. How do you fit that into a logistic regression framework? What you can do is you can have 4 columns. The first column is I. Each word a column. Each word a column, and then you are going to transform the text data into a bunch of dummy variables. 1, one for, I mean, all the 1 for this data point, yes. You only need 4 columns for up to this point. But you have the second data point here. No. Meaning I don't support. No, that's negative for sure. If you were to convert that in the same way, you have to add another column. Yeah. Because it's a unique word. So a bunch of dummy flag variables, and then this will be coded 1, but no will be coded 0 in the first data point. Yeah. That's the way flag variables work. Then you will have to have 0 otherwise. So if you process 100 of these, you will probably have 100 columns. And now it's getting close. You have some columns to work with, all with 0 and 1. Isn't that a data set that you will be familiar with? These are input variables. It's just these input variables, their meaning is their label. And there's only 0 and 1. These are flag variables. So you include these as input features to logistic regression to model their relationship with the label 0 or 1. There you have it. It's a logistic regression model. Okay. So with 100 data points, you can do it. Think about if you have 1 million. How many columns will you need? I mean, as many as how many English words are there? 100,000 maybe. So think about including 100,000 columns into the logistic regression. And good luck. So that's where you hit the limitation. So the language model is basically trying to do better than this. So how to improve and where to improve is basically the dimensionality. There are too many columns to efficiently summarize the documents. With 100,000 columns, the model may not do well, and the model can only do a predictive a prediction. That's it. You have to train it. You have to label it first. You know, we don't have many labeled data sets. So with simple framework like this and with the supervised modeling, it can only do a limited job. To better mine the massive text data, you need to have novel algorithms to be able to do unsupervised learning. Come up with patterns, come up with relations, come up with separations by itself, by seeing the differences. So that's really the purpose. Okay, I need to clean these. Can I clear them quickly? Hide. Great. Right. Okay. So Latent Dirichlet Lda is an unsupervised model. It has a framework that can allow you to summarize or categorize the different articles into a limited number of groups, let's say. And the process leverages the words that appear in different documents. So basically, it looks at the co-occurrences of words, basically. If words co-occur in a set of documents very frequently, they are talking about the same thing. And they are conveying the same underlying domain space. And if this domain space is captured frequently in these bunch of documents, these documents are talking about basically the same thing. So that's the idea behind it. It leverages the co-occurrences of words in documents. There are these bunch of different concepts, and with these different concepts, there are different data objects behind them. You will need to understand what they are. Be familiar with these names, understand what the underlying data is, and how these data allow you to put together the relationships. The original group of authors about this algorithm is 3 persons. If you wonder who that is the very famous person that's very vocal about machine learning. This is Andrew N. If you know who Andrew N is but didn't realize, he is one of the original authors of this paper, of this model, basically. And I think that's where he really began the career in data science. I mean, in machine learning. Okay, so it solves the dimension. The model builds on earlier language models, latent semantic indexing. Right, so there are several things here. These are the things. 4 things. You have term frequency table, also call it feature vector matrix. Term frequency focuses on the terms and the values of the data, the data object, the matrix, is the frequency of occurring of that word, of that term. Term is word, word is token, same thing. Frequency of the term occurring in a particular document, right? So the structure of that is the number of rows, same as the data set. We have 15,000 reviews here. So the number of rows of the term frequency table is 15,000, each row corresponding to each of the review. You have the columns, each column represent a feature. A feature is a token. It's a unique word that are retained in this model. We only retain a limited number of, we cannot retain 100,000 of them. We have to limit ourselves to a certain thousands, up to 10,000. So this table is very large. The number of rows, same as the data set. The number of columns, same as the number of features that we retain. In this case, we use 5,000. We stick with 5,000 as a typical number. That's term frequency table. And the values of this table is how many times that word, which is indicated by the column, how many times this word occurs in this document, which is indicated by the row, right? So you have the document and the column. You have the document and term combination. So how many times the term occurs in this document after cleaning? That's the first concept. Feature names list is, how do we, wait, I'll get to that. This is a list of different concepts. I'll talk about each of them in more details. Feature names lists is a list of pairs. It's a list, but helps you to go from point A to B. Point A is if you know the features index, it's a number. If we have 5,000 features, the number goes from 0 to 4,999. If you know the number, which corresponds to the index of the table, term frequency table, the index of the column. The index of the column refers to the index of the term, right? So if you know that number, you can recover the exact term, Python, things like that. So if you know the index of the term, you can get that exact word based on this feature names list. And then you also have this result. This result is the direct output from the Lda algorithm. After the Lda is fit to the data point, to the data set, you have a direct result. This result describes the document. So it has a similar structure as the term frequency table. It has a number of rows that correspond to the data set, 15,000 rows here. But the columns are simpler. This describes the distributions of the different topics. Now we have to talk about topics. Lda is a model to summarize vast amount of documents into a limited number of topic space. It calls it topic, but it doesn't have to be topics. It's just dimensions in the high dimensional space that you use to understand the meaning of the document. So you can say that's topic. You can say that's concepts as well. The name is subjective. You give whatever name it is. The original authors describe it as topics. I think, and that's what sticks. Topic is probably very appropriate to describe whatever the concept is. So this table has the number of rows as the same as the data set, but only the number of columns that you specify as number of topics. We go with 10 topics for Yelp data. It seems to be 10 topics are the magic number, but not really. 10 is easy to work with. That's it. You can have 20. 20 is much more to work with. That's it. So if we say there are 10 topics here, then this table has 10 columns, and the values of each of the cell in this table is the probability that this document is describing this topic. So for every document, you will have a distribution of different topics. The topic with the biggest probability is what the model is thinking this review or this document is describing. So we'll look at specific topics. What are they? And it highly depends on the data set. And the last one, after you train the model, the Lda model, you extract the components. And this is what. So think about it. What have we talked about? We have talked about documents. What is the document? A bunch of words. Documents. Each document is a bunch of words. Our data set is a bunch of documents. Each of the document is a bunch of words. We have the term. What is the term? Term is the words. We have the topic. What is a topic? Topic is more subtle. Topic is what links the term and the document, actually. Topic is the latent space of the words and documents. I haven't confused you yet? Anyway, I mean, I'll describe more, but actually, but topic is what the model is trying to solve. It's the latent space that describes the high dimensions. I try to reduce the dimensions into topics. So a document can have multiple topics, right? Each with a set probability. If you pull a CNN article, if the title says former President Trump, it must be talking about politics. So it's highly likely it's talking about politics. If you read it, you'll be more, more confident. It's talking about politics. But in some of the paragraphs, it's also talking about the former first lady, right? Also Trump, right? So a higher likely topic is politics. A less likely but not entirely impossible topic is about family relationships. Okay, how Trump is not able to, maintain a marriage. Anyway, I'm not talking personal. That's the way it is. But anyway, so, the topic of politics is assigned a probability of 0.8. The topic of family matters is assigned a probability of 0.15. Both topics are possible, politics more likely. So you see what is topic? That's the latent space that's reflected by these words. But the question is how does a computer learn what these words represent? That's a tricky question to think about. How does the computer learn? How does it doesn't know who Trump is, but somehow it can figure out that whenever you talk about Trump, it's politics. There's no other way. But it could be also something else. Less likely, but also possible. Based on the words. Again, it's all based on the words. Computer is not trying to trick you. Computer is learning the associations between the words. How does it figure out? It figures out that based on co-occurrences of terms, basically. If all the articles that talk about Trump is talking about politics, there's no other possibility. It's about politics, right? A small portion of it talks about other things. So then computer figures out there's other things that are also possible, but with less likelihood. So that's the way it figures out that. So then what is this component? This is a topic word. So you have something that describes the document. You have something that describes the words. You also have something that describes document and topic together. But you don't have something that describes topic and word. So this one is describing that relationship. So you have everything covered here, different concepts pointing to different things. And altogether, you have a good framework. Sounds good? All right, let's talk about more specifics. Let's get on to the technical. So this is a term frequency table. It's also called feature vectors matrix. It's basically what the bag of words model is. So what does that mean? You have a specific document that takes one row of this matrix, one row. You have a specific feature that represents a column. Say this is Python as a feature, right? So term frequency table describes the number of times that Python appears in this document. As simple as that, term frequency. Why is it called feature vectors? Every column is a vector. Every column describes a feature. So that's why it's feature vectors. It's a matrix. So it's a lump sum of all the features that's included in this document. So let's think at a higher level. If you take column sum, what do you get? A bonus question. If you take column sum, what do you get?
The number of features, total number of features.
Like 5,000 features? If you take column sum, you will get as many items as there are number of columns. You'll get 3, 100, 50, 7,000, 1. What are these?
Like how many times they're repeated in the document? The words are repeated.
In which document?
In the rows, in one particular rows, how many times the word Python is repeated?
Right. So that is one row.
Yeah.
But if I take column sum, this is the sum of this column. If I take a sum, I basically get all the sums. So what are these numbers?
Total number of count that Python, like how many times the word Python is repeated in the whole document?
In the whole, not document, data set.
Yeah, like
in the whole data set across all the documents, right? Okay, great. Let me ask you one more question. If I get the column sum, it's a vector. I sum those up. I get a number. 1,000,000. What is it? I get the grandson of this matrix. What is it?
All the words in the data.
Frequency of what? Huh?
I say all the words in the data set.
All the words. Let's say if English dictionary has 100,000 words, is that the number you're talking about?
Yeah.
Think more. I can have Python appearing twice, and that 2 times will be counted. So it's basically the word count of the data set. Yeah? Every cell is the number of times the word appear in one document. I take the column sum. It's the number of times this same word appears repeatedly across all the document in the data set, but this is only one word. If I take the sum of that, it's a word count, basically, of this data set. Okay, yeah. I think you deserve points. Let me do that. Okay. Great. Okay. It's getting more fun, huh? Anyway, so that's what this table is doing. This table is important as sort of a raw input to the model, basically. This is one of the raw inputs. The advantage, those are, sort of, they carry a lot of information. If 2 words have a peak number of occurrences in only these documents, you can almost be sure these words co-occur more than random chance. And these words are talking about the same thing. You can figure out something here. But the problem is domain expertise or domain focus. If these are all about politics, you will see that word politics a lot. And this politics word is not a stop word, and it will not be removed. So in this context, is this word any useful? Not really. It's happening too much. It's as if saying one thing that's obvious. This data set is describing politics, but I don't need you to tell me. I know this problem is about politics. I know the data set is about politics. So because I collected these political articles, so that word that appears too much doesn't help. But this word is going to appear too much a lot here as that single column that has the most count. So so this table is not standardized. We need to standardize it to let the higher numbers indicating useful information for sure. You want the numbers to be monotonically indicating something. That would be better. And another assumption behind this, that's why it's called bag of words, is it basically ignores the word order. So look at these two sentences. Python is superbly interesting, for sure. It's positive about that. Superbly. It's actually somebody's name. Okay. Superbly is saying, is Python interesting? No idea. So the sentiment that's conveyed by these two sentences are completely different. And yet, if you reduce it to term frequency table, it's exactly the same thing. So that's where model is not going to make a differentiation based on this model, and it cannot detect any differences. So bag of words have limitations. That's where the limitation is. But I think, you know, in common problems, you are not getting this very often, where the combination of words is going to give out 85% or 90% of the true meaning. And the remaining 10% or 15% is tolerable. It's fine. It gets the job done without differentiating these nuances. So bag of words is the most commonly used language representation encoding process. This is the encoding process that people use to solve basic problems, or at least it can serve as a benchmark model. Any other algorithm that can beat that is good. But the basic assumption here is bag of words model. You'll have some problems in the homework that asked about that. You know, what does that really mean? What does bag of word means? What order doesn't make any difference. That's what bag of words mean. You know, you put a bunch of words and put it in a bucket. The order is scrambled, but the model treats them the same. Once you have the term frequency, now let's talk about the document frequency. And document frequency is not talking about documents per se. It's still talking about the terms. We are trying to come up with a measure of the terms that where the value will monotonically increase if the significance term increases. So the higher value means better importance for the word, for sure. Using term frequency is not going to solve the problem completely, right? Because you know, due to domain focus, some common words to this domain is going to appear very often, but it doesn't say unique information. So what we need to also consider is how common is this word being used across the documents. If it's appearing too often in all the documents, it's not useful. It's not unique. We need it to be moderately unique. We need to be unique to the sense that not a lot, but some, but definitely not only one article as well. So no extremes. So document frequency is describing the number of times each of the term appear, or the number of unique documents. It's not the word count. So we'll remove the repetition. Number of unique documents that has this word. If we have 10,000 data point, and this word appears 10,000, which means it appears in every document, it's not. It should be discounted. It's not very informative. If the document only appear in one, like, you know, if it appears only once, it should also be not informative. It's too unique. It has to be in between. But, you know, we have to have a scale to measure it. The solution is 10,000 not very good, 1 not good, but 1 is at least better than 10,000 because it's on the unique side. So we take an inverse and scale it properly. This is the inverse document frequency of the term that gives away additional piece of information about the uniqueness of the word, right? So the inverse So we put them together. We put the term frequency and inverse document frequency, put them together, it becomes a composite matrix that describes the uniqueness or value of the terms. That's why you see term frequency, inverse document frequency. So that's the function. That's a formula that includes both components. We will work with that. This is similar to that, dummy variable matrix, but in a sense better, because it's not a simple count. A simple count is the term frequency. It's better than term frequency as the additional information of word uniqueness. So, the term frequency TF IDF is better than TF alone. Okay, now so let's have another question here. You will have a better advantage if you have prepared for, if you have reviewed that slides demo, if you have run the code, if you have played with the code. By the way, I uploaded that newer version today again. The several cells in the bottom have been updated, but I'll point out that when I cover that. Okay, question for fun and for bonus. In the Yelp data set, after cleaning all the non-stop words, after cleaning on all those stop words, after cleaning the punctuations, after doing all the pre-processing, for those real words, I'm asking about 3 words. A word that has something to do with the stuff that you go to a restaurant for. These are the words that are being used in reviews. Think about when you read the reviews about restaurants, or when you write reviews about restaurants. A word that is used the most often that has something to do with the stuff that you go to a restaurant for. This is any restaurant. Food. Yes. Did you?
I said eating, but that's it.
Oh, okay. Food. Yes. Double. Okay. That's good. Let's go on. A word that describes the stuff. It's not saying. It's not referring to the stuff. It's describing. Like, how is it? It's describing how is the stuff that you buy in a restaurant. What do you say? Quality. No. Taste. I think it's not on the right direction. So let's say adjectives. Delicious? Not really. Because not many people can type delicious. It's too complex.
Good.
Good. That's good. Yes. Think about Yelp people. Don't overthink about it. By the way, I write some reviews for Yelp as well. So let's see. Where are we? Yeah. Okay, so that's the second one. And where's the pen? The third one, it has something to do with the environment. Huh? Hygiene? Clean, not clean. Okay, think simple. Okay, no, this time it's not adjective. Huh? What? Plastics. Good one, but no.
Straw.
Straw.
No.
No.
Carrier?
Actually, not specific items. It's a very generic word. Very, very, as generic as you can get.
Sitting.
Sitting.
Dining?
Service.
Not good. Good. Huh?
Dining?
Dining. No. Dirty? No.
Patio.
Patio? No.
Service. Waste.
Waste? No.
Classy.
What is that?
Classy.
What letter does it start with?
Beautiful. Beautiful.
Huh?
Beautiful environment.
Due to the environment?
Beautiful.
Oh, beautiful. Not adjective, actually.
Oh.
And what did you say, Angela?
All right.
All right. But that's an adjective. Something like that. The word is not adjective.
Reflective.
Not receptive.
Okay. Ambience.
Ambience?
Yeah.
Eating.
Food? Not eating.
Fine.
We had food before. Food is the first one. Place. Place. Yes. Place. Common word. Like this place is good. That place sucks. You know. So, that's fun. All right. But of course, I realize these descriptions might have misled you, but that's as close I can come up with and without giving it away. I'm this close to giving it away, but actually, I discovered something. When you ask Bauer students, you tend to overthink. It's like playing chess. You think your opponent is super smart, and you try to outsmart. In the end, they don't know what to do. But anyway. Okay, so hands-on. How to do LDA. These are more on the theoretical side. What is the LDA model doing, basically? It tries to describe, or it has a theory, actually. It has a theory about what we call academics working on data, working on modeling. We call it DGP. Is the underlying process, which is theory, underlying process that generates the data that you observe. You're gonna have a theory to survive in academia. So that's a theory. But basically, this is how things happen according to the theory. So you have a document is a bunch of words. You have, I like this place, this document. But a document doesn't contain a list of random words. These words are picked based on some underlying pattern. And what is it? The concept is topic. You are trying to describe something, invisible, something abstract, whether or not it's an affection, liking, or approval, right? These are the concepts. To express your approval, you search for words to describe what you want to say. You come up with words, I like this place. So the theory is you pick the topic first before you pick the words. That's, reasonable, right? Although we really don't think that much. We just write. But that's the theory. But if another person is going to review this restaurant, the topic may not be approval or liking. It can be something else. Story. The topic might be story. So then the writer search for words to convey this topic. That's the theory. Whether or not you buy it or not. That's the theory. That's a data generating process behind it. And of course, it doesn't have to be right, but it's a nice story about the theory, right? And that's as much as I'm going to talk about. Okay, so let's switch over to the hands-ons. So basically, getting to know these objects, 4 objects basically. LDA. We actually use some utilities that are not from GenSim. GenSim helps actually pre-processing it. For LDA, we use that utility from sklearn, actually. Anyway, and this is needed so that we can split it. You can very easily write a split function on the fly, but this is so that you can set up a place where you can, use more complex tokenizing functions here to replace that simple split. Okay, now TF, term frequency. TF describes the words in the document, the terms in the document. So TF has 2 components, the document and the term. We use this count vectorizer. It's basically, you're counting the frequencies, term frequency. Count vectorizer specify these parameters, and this has something to do with Uvi's question here. What decides who gets selected? If you have 100,000 words, unique words, what decides these 5,000 are being selected? And there is this is the custom tokenizer that we provided there. It simply splits the paragraph into 1 gram words after the data has been cleaned. Lowercase no, because we already lowercased it. Max DF. Max document frequency. Max document frequency. It's a threshold you set that will help you eliminate any word that appears more than this frequency in documents. So you will get rid of everything that's more common than this. 0.5 means if a word appears in half of all the data points, which is here is 15,000 reviews. Half of them is 7,500. If a word appears in more than 7,500 reviews, this is too common. We'll get rid of it. So that's one. And then after getting rid of that, you probably also have too much. You have more than 5,000. Then you give a upper limit, 5,000. You retain 5,000. But who decides? Again, who decides what retains? It's based on it should be based on TF-IDF. So whichever is top on the list will get retained. Lower on the list will be dropped. So in the end, we have 5,000. So these 2 parameters will actually decide how the model performs. These are 2 key parameters. This is where sklearn objects work. You define the object, and then you use it to fit into the data and get the output. The output is the term frequency table.
So in custom tokenizer, can we, so you mentioned text.
Mm.
If we mention the number, can we also give the range of that number?
Numbers, to work with numbers, you can use alternatives that are much easier. You don't have to mix numbers with here. So again, the best way to deal with numbers is to extract numbers separately as separate columns, and then clean the text as the way you would clean text. Don't deal with numbers. Don't mix them together. Mix them together makes it more complex.
What if the numbers, though, are carrying a meaning that's like a string, like talking about 7-Eleven gas stations?
Oh, those should be retained, I think. Like if it's 7-Eleven, like there are no hyphens in it. If there's hyphens, it will be broken. But you can control the nuanced way that tokenizing works. You can probably ignore the hyphens, which means to retain it. Or you can treat hyphens as a punctuation to separate before and after, and to break them into two words. 7-Eleven with hyphen, it becomes 7 and 11.
But you know what I'm talking about? The convenience store, that the name of it is like 7-11.
Okay, not okay. So two numbers. With generic approach, it's likely dropped. It will be
But you don't want
eliminated.
that to be treated as a number either.
Well, if it's 7-Eleven, the pattern is very clear. You can search in the entire column and make a flag variable. If this review talks about 7-Eleven, the flag variable is 1. If not, it's 0. It's going to be majority 0. Only a few reviews talk about S7-Eleven, they are 1. And that's it. And then when you clean those texts, you can safely ignore 7-Eleven and let it clean, right? So use this approach to deal with special symbols. Symbols that might be clean out if you don't treat it differently, so then treat it differently on the side. But don't mix it together with the text cleaning. Yeah. By the way, if you clean it on the side and you have a like special indicator, if you will, then I think you can define your own term. Like with the standard approach, you have a dictionary basically. A dictionary contains all the terms that remain in the clean text, right? So let's say here you retain 5,000. There are 5,000 terms, but 7-Eleven has been cleaned. You can add one here to make the 5,000 first, and that concept is 7-Eleven. And you can add that term frequency into this term frequency table, have one more column. I think that's doable, but that's a slightly additional work. But if you set it up right, it should be doable. Should be doable. Nice thought. Right. It remains a question whether it's an empirical question whether or not it's worth it to think about these. But I think it's a good idea to try at least, and to find out if over and over these special treatments don't provide a return in terms of model improvement, then you'll start bothering, right? But if they do provide returns, that will be novel implementation. Very nice. I think the model, the tool is flexible enough for you to add a special term to complement the automatic set. I think it's doable. Okay, so the term frequency table, think about the structure, number of rows and number of columns. Is it right? It's right? And what is in the table? You print the first 2 rows and first 5 columns. It's all 0. What does that mean? Not really. It's term frequencies.
Values, they don't have the count.
Right. These words don't appear in the first 2 reviews. And there are going to be a lot of zeros, like a lot of zeros, because you have 5,000 columns. if the first review has 100 words, it's only going to have up to 100 non-zeros. The rest, 4,900, they are zeros. This is term frequency. It's highly sparse matrix. And it just happens to be like the first 5 columns refer to the 5 words, right? These 5 words did not appear in this document. If we randomly pick, if we take the first row index is 0, and we print the review text, this is the one that's the cleaned paragraph, right? So we're trying to figure out for the first word, we're trying to figure out the column index of this word in the term frequency. Which column is it? And then we're going to take a look at the term frequency in that term frequency table. So the way to do that is recall that count vectorizer is the model that keeps a record of all the vocabularies and and assign a unique number to each word. So after you have trained it to the data, you get the vocabulary. It has an underscore. Don't forget about that. This is an attribute. And this vocabulary is basically a dictionary. A dictionary that looks like this. A dictionary is basically a bunch of pairs. You have a key and value, And here the key is the terms. So if, let's say, this is an example because A would have been cleaned, but to make an easy example, A has an index of 0, B has an index of 20. These numbers refer to the column index of the term frequency table. So that's why I use that vocabulary, and to provide the key here, key is happened. I want to know the column index of happened returns 2001. It's one of the 5,000 columns, right? Its index is 2001. If I use that term index, I use this first row index, which is 0, and use that column index, I get the value of that cell in the term frequency table. What does that mean?
The word is present.
Hmm?
The word is present.
The word is present. Not exactly.
Indexing the word where it is located.
Not exactly. That's indexing the word.
Oh, no. In terms of like in a statement where it is.
No, word order doesn't matter. There's no word order. So what is one? Think about what this table is about. Term frequency. So what does one mean?
It is one time it has appeared.
One time, only one time. If happened appeared twice in this entire review, it would have been 2. So that's term frequency, right? And more, a little bit further, this is, okay, so this term frequency table, it's a SciPy matrix. The way that you slice it is, or index it, is different from the way that you index pandas object. So don't use iloc. Don't use loc. It doesn't work. It's still like an array. So you can use row and column index to index that. But if you want to slice it, you cannot do that with the original form. You have to turn it to arrays before you can slice it. So when I turn it to array, I get the row, I slice it 2 items before, and then 1 item after, it's actually, because it stops at the 2 times after. So I slice this 4 items. Now, the term index is 2001. 2001 minus 2, slicing until 2001 plus 2, I get 4 term frequency. My question for you is, which of these numbers is the term frequency for happened for that first word in this review? Happened. Which one of these 4 numbers are the term frequency for that happened term? As in this one? Mm-mm. And there's only one more possibility now, right? It's the second one. It's the third element, right? And the reason? I mean, it cannot be 0 because, happened. It's not at least once. But why is it this one, not this one? If you say this is the row index, it's the same. But if you say 2001, that will index happened, right? But if you take a slice, it becomes minus 2 to plus 2. Now it becomes 1999 slice 2003. Still 4 items. 4 items. When you subtract them, it's 4 items. So 1999, basically 2000, 2001. That's a third element, right? So that's this one, not that one. But you wonder what this one is. It's actually happen. Happened once in here in this review. I think that's happened. Let's see. So there's a happened and there is a happen. Because computer thinks it's 2 unique words, right? So it will give it 2 different indexes. And you can actually see that when a dictionary compiles the list of words, in the end, it's going to rank it based on alphabetical order. And happen is just one place earlier than happened, right? So if we were to extract for index 2000, then you can see what word it is. If you do index new, which is index -1, you get happen. The index is 2000. So happen and happened, very close, which is alphabetical order. Okay. One more? One more question? Yeah? Okay, let's see. Oh, actually, no more. This is the answer to those questions. Right. So the way you get the 3 most frequent words, how do you get that? Here demonstrates the process. You basically leverage information from the term frequency, right? You leverage the column sums, right? You first get a column sum, which is sum of the number of times each word appears in the corpus. So that's column sum. So you transform it to array and take the sum according to axis 0, which is a column sum. Take the column sum, you get a factor of 5,000. And these 5,000 numbers describe the number of times each of these words appear in the document. And then once you have that, that's the column sum, this is a NumPy array. So you sort it, but when you sort it, it's ascending order. So you take the last three, slice from the third to the last and to the end, and then you reverse the order. That's a reversing. So you get a descending order of 3 indexes. These are the indexes behind the words, actually. So you get 3 indexes, and based on the 3 indexes, you take it from the feature names list. Feature names list is a list of actual terms where their index position corresponds to the index of that column. It's a little bit too much to think about, but anyway, based on these indexes, you get the 3 words: food, good, and place. That's the most common words that's used. All right, so the rest, I think there are videos you can talk that you can watch, but basically you specify the number of topics. For the homework, we use 10 because 10 is easier to work with. But we're going to experiment a little bit here. Use the LDA function, define LDA, and well, actually, the LDA training process is actually not something to experiment with. It's a standard process. Once you have the TF-IDF, it's almost decided that what the outcome will be. But the trick thing is how to get those feature word feature names list. How to get the feature names list. How to get the topic word matrix. And how to get the ultimate results. Ultimate results is here. When you train it and fit it to the data, you get the result LDA. That's the description. That's the distribution of the topics for all the documents. Then here the process goes through how to extract different things, how to get topic word distribution table, and how to use these indexes to find those words. Same exercise with the top 3 words. So in the end, you can have this by following these codes. You can get, for each of the 10 topics, what are the 10 most commonly appearing words. And so for each topic, you get a list of words. These are the most common words under this topic. Then you will need to figure out what this topic is, because this is a latent space. It's not defined. You need to. It's not mine. Anyway. So based on the list of words, you can come up with the idea of what the topic is. But there's an experiment here. So the way the term frequency table is made, the count vectorizer, we use a threshold of 0.5. Anything beyond that is removed, but anything below that is retained. That can still lead to problems. You can have things like, food. For Yelp restaurant reviews, it's definitely about food. If food is appearing in any of the topic, is it really informative? And the problem is food appears too much. How many times does food appear here? Let's see. In 6 of the topics. Let's look at the topic. Topic 3, food, great, service, place, good, stuff, friendly, love, nice, lunch. What are you talking about? I don't know. And like, food, place, time, better, location. It's a little better, but basically good. That's all. So these topics are not really separating from each other. Topics should be distinctive. If there are too much overlapping, it doesn't help, right? So to solve that problem, you want to remove those words that appear too much across the documents. So the one parameter to tweak is the max df. So I've done that. If I reduce to 0.1, it's very low, but not low actually for this context. You want to have a smaller number. 0.1 is better than 0.5 for sure, because 0.1 is still 10% of the reviews. Anything that appears in 10% of all the reviews, it may not be as unique as you need. But let's go with that and see. With that, you have a much better separation of the topics, the first one. And based on the previous version with the Limitization, these are the topics I came up with. But it doesn't have to be the good one. You know, the order may have changed, or the topic space may have completely changed. So let's see. You tell me whether or not topic 0 is about fried chicken plus rice, pizza, minutes, asked, said, told, manager, table, customer, took, people. Yes or no? There's no chicken anyway. There's no chicken and no fried. So this is not. This is probably talking about pizzeria. Okay. So the order of the topic space has changed. Is the second one cheap pho all day, like, you know, Vietnamese food? Rice, soup, lunch, Thai. Well, Thai can be Thai as well. Fried pho, bowl, dishes. That's right. Doesn't have to be cheap, but it's pho, you know, Vietnamese or Thai. What about the second? Topic 2, fresh sushi rolls. Roll, sauce, salad, cheese, salmon, bread, grilled, tuna, rolls, shrimp. Yes or no? More or less, yeah. I mean, at least compared to the other topics. So you can go through the list. There's definitely room to improve the interpretation. This is the results of the model. This is your interpretation. You know, results of the model has correct answer. Interpretations does not have correct answer. It's all subjective, right? But make reasonable judgments, and you'll have a homework question to do that exercise. The homework question will not deal with Yelp reviews, for sure. The homework question will deal with academic paper abstracts. So the kind of topics you can imagine, lab, you know, experiment, or some kind of materials. Okay, so good luck. Any questions? Well, let's call that a day.